We reject the challenge.
Want to change problem number 1.
We reject the challenge.
Want to change.
这跟下午没关系，这跟下午没关系。下午登记的最事情，
We want to change the problem number 7.
这跟下午没关系。
We will count.
We accept the challenge.
Okay, great. Your preparation for finding everything right on the campaign name.
the reporter would like to skip the time.
Okay.
Honorable juries and fellow competitors, I'm the reporter from Team Excel here. Today, I'm going to report problem number 7, lunar cannon. This is the problem statement. Two rulers are tightly held against each other. A round projectile, for example, a plastic bottle cap or a ball, is inserted between legs close to one flare end. When extra force is exerted on the surface of the rulers, the projectile is ejected at a high speed. Investigate these effects and parameters that affect the ejection speed. And about the main focus, we will mainly focus on how does the energy transform throughout the ejection of the ball, and how does the extra force exerting contribute to the ejecting velocity. This is the presentation outline. First, let's talk about the observation. This is our experimental setup. Since the problem statement has mentioned to exert a force on the surface of the rulers, we use electromagnets to release an iron ball as the acting force on the surface of the rulers. At the same time, we can also make sure the iron ball will hit symmetrically on the surface of the rulers at the same time. This is the observation video. As you can see, the projectile experiences a rapid acceleration as the force is applied and reaches its ejecting velocity. And from the charts, we can know, corresponding to the problem statement, the speed we mainly analyze is the initial ejecting velocity. Now, let's move on to the qualitative explanation. Before the iron ball strikes on the surface of the rulers, the projectile is inserted into the rulers and deforms them, which creates an F1 shown in the diagram. And in this case, the static friction prevents the projectile from slipping out. This allows the rulers to store potential energy caused by bending, as you can see in the diagram. Also, this is the critical condition of our experiment, which is when the tangent theta is not larger than the static friction coefficient. And after the iron ball strikes on the rulers, as you can see in the video and the diagram, when applying additional force, the elastic deformation of the rulers increases, and the friction is exceeded by the restoring force of the rulers. And when the ruler snaps back, the elastic potential energy converts into the kinetic energy of the projectiles. So the energy transform process will be like this. The potential energy of the rulers will become the kinetic energy of the rulers and the ball. Also, we have considered the dissipation. Now, let's move on to the theory part. We use uniformly beam theory to describe the deformation of the rulers under external force. Since the ruler is typically fixed at one end, so it can be considered as a cantilever beam. We discuss the bending moments in two phases. One is from the fixed point to the striking position. Another one is from the striking position to the edge of the rulers. Assume we apply force at B. When X is between the fixed points to the striking position, it will be affected by the additional force exerted on the surface of the rulers, and also the normal force provided by the ball. When X is between the striking position and the edge of the rulers, it will only be affected by the normal force provided by the balls. And also, about the curvature, we can derive from that formula, and which is the bending moment divided by the Young's modulus and second actual moments of area. And after integration, we can get the deflection of the beam. Now, let's talk about how elastic potential energy work and transform in the system. By the formula we derived previously mentioned, we can get the formula, after integration, we can get the formula of the potential energy. This equation describes how does the elastic potential energy storage during the deformation process. And the overall energy transform process will be looked at this. The kinetic energy of the rulers and the balls will, and plus the dissipation energy, will equal the deformation of the potential energy of the rulers. And we can assume that the dissipation as the alpha, constant alpha, times the potential energy. So the kinetic energy in this case will be 1 minus alpha times potential energy. And at the same time, we can know that the ratio of the kinetic energy will equal a constant beta times the ratio of the mass. And about the constant alpha and beta, we can obtain it by the experimental data. So derived from the above mentioned, we can get the ejecting velocity of the projectiles. And this is the fitting of the constant alpha and beta. As you can see in this chart indicates the total energy transform process. We can plot this chart based on our experimental data, which is how our theory predicts the potential energy and transform into a real-life kinetic energy, which is the kinetic energy of the rulers plus the kinetic energy of the ball. So we can fit the alpha will roughly equal 0.48. And the chart showing there, as you can see, the y-axis represents the kinetic energy of the projectile. The x-axis represents the kinetic energy of the rulers. As above previously mentioned, the ratio of kinetic energy will equal the constant beta times the ratio of the mass. So we can fit the beta will roughly equal the 0.043. Now let's talk about the experiments of our phenomenon. The first parameter we did is different striking position. When we change different striking position, it will create different bending moments to the rulers. When the force is applied further to the fixed end, the ruler has more stored elastic energy, leading to a faster projectiles. And as you can see here, the experimental data is slightly lower than the theory line. And now it's the explanation. It's because the constraint caused by the ping pong ball positioned at the end of the rulers, which means the deformation space for the rulers is too small. And the second parameter is the pendulum release height. When we change the pendulum release height, it can generate a different force acting on the surface of the rulers. And the force magnitude will obtain by checking the impact and rebound velocity of the iron balls. When the increasing force is applied to a ruler, the potential energy stored increases, and the minimum ejecting velocity shifts to the left. Now, let's talk about the deviation analysis as previously mentioned of the constraint of the projectiles. When the striking position is close to the ping pong ball, the ruler can't reform much. Therefore, the energy converted to the ping pong ball significantly decreases, like the chart showing here. And also, since we have done the measurements of Young's modulus of different kinds of rulers, as you can see in the video, that's the experimental process of our. We have recorded the different deflection corresponding to the different force application, and plot the deflection and the force relationship in this chart. As you can see, these two straight lines indicate the linear relationship between the deflection and the force. And this is a very important value for us to further calculate the Young's modulus. And that's the chart showing the calculations. We have derived the Young's modulus of iron rulers and aluminum rulers, and of course the second axial moments of the area. So with the third parameters we did is the materials of the rulers. A smaller axial moments of area and Young's modulus leads to greater ability to store and release elastic energy, affecting ejection velocity. So once we have the materials properties, this includes Young's modulus and second axial moments of area, we can predict how does the different materials of the rulers affect the storage of the potential energies to the experiment. Now, let's move on to the discussion. Since we use pendulum as the active force on the surface of rulers, we would like to discuss about boundary condition analysis. We mainly divide it into three phases, which is the successful ejection and failed ejection, and the ejection caused by vibration. Let's look at the vibration videos here. As you can see, the round projectile didn't eject immediately after the iron ball hits the surface of the rulers. Instead, the round projectile is ejected by the vibrations of the rulers. So we consider it as a boundary condition. Now let's look at the failed ejection videos. As you can see, the pendulum's force acting on the surface of the rulers is too small for the system to exceed the critical condition we have previously mentioned. So in summary, we have divided the condition into three phases, which is the ejection caused by vibration and failed ejection, and of course, the successful ejection. And another boundary condition analysis is the effects on friction. We have tested 4 different materials, which is the plain papers, tracing paper, and of course the iron rulers, which is the original condition, and of course the plastic. And the way how we do it is we wrap different materials around the projectile, like the picture shown here. And we have observed that the boundary conditions shift to the left with stronger force, and ejecting velocity increases with smaller friction coefficient. Like you can see here, the plastic have the smallest coefficient of the friction. And this is because the converse rate increases under this kind of condition. And we have observed very interesting phenomena, which is when the uneven force applied on the surface of rulers. The way how we do is change the different release heights of the pendulums. As you can see, we have fixed the down part here as the 8.5 centimeters. And the control variable is here. And the upper part is the change variable. We will change different release heights to create different force acting on the surface of rulers. And we have observed that the ball tends to eject toward the upper side, which is the last force applied. And we also have observed that the self-rotating of the ball was observed. Now, let's move on to the conclusion of the experiment. Corresponding to the main focus, how does the energy transform throughout the ejection of the ball? By this mathematical formula, we can know how does the elastic potential energy storage during the deformation process of the rulers. And this is the force diagram from top view, and that's the force diagram from the front view of our experiments. And the overall energy transform process will be looked like this. The potential energy of the rulers will transform into the kinetic energy of the rulers and balls. Also, we have considered the dissipation. The second main focus, how does the extra force exerted contribute to the ejecting velocity? As previously mentioned, we have changed the parameters of different release heights and different striking position. And we have observed that when the force acting on the surface is bigger, it will tend to have a faster projectiles. And we divided the condition into three phases, which is a successful ejection, failed ejection, and vibration caused the ejection caused by vibrations. And that's the boundary limits of our experiments. And that's the end of our report. Thank you.
Okay. And the question of owner to reporter.
First, I would like to ask, please turn to page 11. Could you please explain what is the second actual moment of area?
The second actual moment of area is the materials properties of the different rulers, which can be shown as the I'm sorry, I can't find that. So it's the materials properties of the rulers.
Okay. And the next question is, how did you measure the coefficient of friction?
Coefficient of friction we can obtain by the experiment. And as previously mentioned, we have done different materials different materials wrapped around it, and that's the way how we do it.
And is that so you check the beta and measure the coefficient of friction?
We wrap the different materials around the ping pong balls.
So you use all the beta is all the same in each experiment.
Yes.
So did you consider coefficient of friction is a constant?
No, we consider it as influencing factors to the experiment.
I mean, will the normal force influence the coefficient of friction?
Do you mean under different kind of conditions or
under different normal force?
Under different normal force? Yes, we consider it as the same.
Okay. And did you consider damping in the theory?
Well, damping is part of the formula we have shown, which describes the dissipation.
Okay.
Okay. Deliberation of opponent for 3 minutes. Okay, opponent measure flow maximum 4 minutes.
I'd like to uphold the problem 7 rule tunnel. This is a problem statement. Two rulers are tightly held against each other. A round projectile is inserted in between them close to one of their ends. When extra force is exerted on the surface of the rulers, the projectile is ejected at high speed. Investigated the state and parameters that affect the ejection speed. And the key point in this problem is energy transform. This part is the overview of the reporter. For the theory part, the force energy analysis and explain the energy transform. And they use binary spin theory to explain the theory and fit the experiment result. For the experiment part, they do different parameters like track point and release height and the materials of the ruler. And they do deviation analysis, and they talk about boundary condition analysis caused by energy. And for the conclusion part, they use the formula to explain the energy transform, and they mention the extra force effect. And this part is a remark to the reporter. For the adventure part, their theory formula is clear, and they show the experiment video to make us easier to know what you do in the experiment, and they do great theory analysis. And for the suggestions, because you use pendulum to exert the force on the ruler, but that in this condition you can make sure the force that your iron ball hits the ruler, and also the real experiment lack of data. And these are points that I want to discuss with you. First, for the theory part, elastic potential energy transform and convert rate, and the unit Bernoulli pin theory, also the cantilever pin. And for the experiment part, the constraint of projectile and boundary conditions affect the ejection. Okay, thank you.
Any discussion for reporter and opponent? For 10 minutes.
Okay, so that's what I just said. You can make sure the force that the ball hit on the ruler, right?
Indeed, we can. Because we have said the force magnitude were obtained by the impact and the rebound velocities. So as you can see, sorry, it's in the breakout. As you can see, by the impacts of the ball, we can calculate the applied force under different kind of release height.
However, you didn't know the delta P, right?
We can predict the contact time.
How to predict that?
Since the acting time, we can, no, I'm sorry, to rephrase my answer, we can do it by the tracker to track the contact time between the pendulums and on the surface of the rulers. So by this, we can know the applied force under different kind of release heights.
So you measure the velocity in the ruler and the velocity go back and the delta T during this period, right?
Yes.
Okay, thank you. And another comment is you say that you consider the coefficient of friction is not a constant. And
To clarify my answer, I'm sorry, I'm misunderstanding the opponent's question. I thought the normal force you have say is under same normal force we have say the ping pong ball inserted into the rulers. However, I noticed that the opponent is just asking about in different normal force, right?
yes.
So based on this, the friction coefficient we need to obtain by the experiment, so we can know it. So based on this, we can predict it won't be the same. So to clarify, and
So do you measure the coefficient of friction under different normal force to enhance your theory?
Well, since the normal force is provided by the ping pong ball, so we have done the experiment to show the effect on friction coefficient, which is the third one, the original condition of the experiment.
Okay, and could you turn to the theory part?
Theory part.
Actually,
You mean
the
potential
potential energy?
Potential energy. Here.
Yes, for this integration. I think that you can only use this integration when you bend a ruler with the force, and the force is and the force goes bigger slowly, and the ruler bends slowly, right? And so you can do integration at the x. But if the force is big at the initial condition, and so the ruler has velocity during the bending. So maybe the energy couldn't be right in this formula.
Well, actually, we have considered the kinetic energy of the both rulers, and the ruler snaps back kinetic energy, also plus the kinetic energy of the round projectiles. And as you can see on the formula here, we have considered in different kind of condition, which is when the fixed points to the striking position, and the striking position to the edge of the rulers.
Okay, and the next question is find the proportion with kinetic energy of ruler and ball is proportional to the mass proportion.
We can know it from the calculation of the mathematical formula.
Could you explain this more?
Okay. Joyce, can I use the blackboard?
Sure.
Since the kinetic energy will equal this, so we can obtain the kinetic energy have something to do with the mass of the ratio of the mass of rulers and balls.
But the velocity of that is different.
This is the phase that we consider in the fitting of the constant data. As you can see, the y-axis represents the kinetic energy of the projectile, and the x-axis represents the kinetic energy of the rulers.
So this part should be mv squared.
Can you refresh it?
So you write that here. So
Yes.
maybe this part should be correct with mv squared.
I don't really understand the opponent's question.
Because you said the kinetic energy is half of mv squared, right?
Yes.
So the energy should be proportional to the mv squared.
Since we have considered the rebound velocity of the rulers and also the kinetic energy, which is the main velocity we analyze for the experiments. So as that, this have considered the velocity of the rulers and both of the ball.
Okay. And so did you consider the friction of the, because you put the experiment equipment on the table, so did
Yes.
you consider the friction force from the table?
Well, actually, from the setup, and since we have this as the fixed points, actually we have made it really tight to the rulers. So we can ensure that the space under the rulers won't have the direct contact area with the wooden board you have mentioned. So like this fixed point, it has tightly fixed the rulers on the upper parts of the fixed point.
There's a problem. Because it's tightly attacked the ball,
Yes.
so it has initial potential energy, right?
Yes.
Did you consider this in your theory or in experiment?
Yes, we have considered it as in our theory, which is when the round projectile is inserted between the rulers, it will have the initial potential energy. And yes, that's the thing we have considered.
Okay. Please turn to the page that talk about the alpha and beta.
You mean fitting of the
Yeah, fitting.
Okay. Here.
Okay. So since that if the alpha is equal to 0 for A, the line fit experiment result, but is the alpha at under different conditions all the same?
Well, this is the fitting under, like, the black line indicates the potential energy we have predicted under based on our theory. And the kinetic, total kinetic energy, this includes the both kinetic energy and the rebound velocity of the rulers. So in this condition, we can know how many potential energy transform into the total kinetic energy. So based on this, we can know from this blue line, they indicate the alpha will roughly equal 0.48. So to answer the opponent's question, it will maintain the same. However, the boundary condition we have mentioned, it will be as the boundary condition we have mentioned, it can be the alpha can be explained under the boundary condition previously
Because
mentioned.
you have changed the material of the ruler in your experiment, so I think the alpha should be different under different.
You mean different materials?
right?
Yes. Yes. The opponents.
And did you measure this?
We have measured different kind of the alpha, and however, this chart we only provided the alpha which under the condition of the iron rulers.
Okay. And did you use ping pong ball in all of your experiments?
Yes.
So did you try to change its
To the passive battle cap?
to change the you did this?
No, like since the problem statement has mentioned that to use a plastic or the ping pong ball,
So
and
you do experiment, but you didn't.
like the reason why is because as the plastic battle cap, it has irregularities around the surface of the plastic battle cap. So we think it's really hard to measure the really influencing factor based on different round projectiles.
Okay.
And also the shape of the ball and the plastic battle cap is different. So we think the factors we need to consider might be two more. However, this is the ejecting speed of the comparison in ping pong ball and battle cap. However, we didn't do further analysis on the battle cap.
I think maybe you can change bottle pack to some other materials that are easier to analyze, such as PVC pipe or 3D print bottle cap. Please turn to page 23. I think the topic of uneven force is interesting in your report. So I want to ask, why did you want to do this experiment? Because the problem doesn't mention this.
This is an interesting phenomenon we have observed during the experiment. Since we use pendulum and we can measure it symmetrically at the same time. And we wonder, what if today we use uneven force that acting on the surface of rulers? What will it change to the velocity and the trajectory to the round projectiles? And so we have done the experiment of uneven force. Since we consider this as a very interesting phenomenon. And as you can see, this tab we tap on the ping pong ball, so we can analyze its self-rotating of the ball, and we observe that. So this means when uneven force is exerted on the surface of rulers, the trajectory in the video, it will tend to eject toward the opposite, which is the last force applied.
So the ball will eject with rotation.
Self-rotating.
Self-rotating. So there will be rotating kinetic energy. And actually, did you do some mathematical analysis in this part of the experiment?
No, actually, this is an interesting phenomenon we want to share. So we didn't do the further analysis on the rotating kinetic energy.
Okay. I think the time is done.
Thank you.
May the opponent summarize the discussion.
So, during our discussion, we discussed some points. The first one is the control of the hit force of the ball hit the ruler. The reporter said that they can measure the initial velocity that the ball hit the ruler and the velocity let the ball go back, and the delta t during this flow period, so they can know the heat force. And the next is the friction coefficient is fixed or not in the same material. And the third one is the accuracy of the energy formula. The fourth one is the parameters affect the alpha and beta, and the different projectile equations, and also the reason of analysis, the uneven force effect, and the final topic that we discussed is the rotating kinetic energy when the force is uneven. Okay, thank you.
Okay. Question of a reviewer who reported on the opponent.
So first I would like to know, so you mentioned the coefficient of friction in the during the cross section. So do you agree that whenever the coefficient of friction increases, the velocity of the ejected speed will increase?
Because actually the coefficient of friction affects the moment that the ball starts to move. When actually the bend it is
It's a yes or no question.
Oh, yes.
Yes. And for a reporter, how do you calculate the bending moment?
About the bending moments, we have. The bending moment is the numerical solutions based on our theory.
Like the simple math function about the bending moment?
It's the numerical solution.
Numerical solution. Thank you. So this one's also for the reporter. So can you restate the energy loss in the system?
Yes, we have considered it as the dissipation.
Like what kind of energy loss? Like you mentioned about the vibration of the ruler and the kinetic energy of the ball.
Well, the dissipation consider the damping and vibration. Actually, the vibration in the boundary condition we have mentioned.
Okay, so do you consider that when the ruler are not fully closed, it will affect the energy loss as well?
What do you mean
Like
fully?
when the ruler pushes a ping pong ball out?
Yes, we have also considered it. Like when the round projectile like ejecting out of this system, the rulers is actually not spaced back. It's
It's not fully closed,
Yes.
so the energy will not be perfectly.
yes, we have considered it in the
Okay, thank you.
dissipation.
And this one is for the opponent. So what do you think is the major reason for the ball to eject?
For the ball to eject is the elastic potential energy of the ruler converted into kinetic energy of the ball.
Okay, and this one is for the opponent as well. So reporters say is they use a cantilever beam model, and what's your opinion about that? Is this a cantilever beam, or do you think it's other beam theoretical
I
model?
think the uniform limit theory is enough to explain this.
Okay, thank you. So the problem statement says that you need to put the ping pong ball at the end point of the ruler. So how do you define the end point?
Well, we define the endpoints. We define at the same edge of the rulers as the radius of the ping pong ball, and we have done the mark on the side of the rulers, so we can know we can measure in each experiment. We can know the position of the ping pong ball is the same.
So do you change the ball's placement as a parameter in your experiment?
Well, no, since the public statement mentioned to put in the edge of the rulers, so we didn't consider.
And this one's for the opponent. So do you think the contact surface of between the ball and the ruler will change?
Yes.
Yes. And
Okay, time is up.
okay, thank you.
Evaluation for review. Can the reviewer take the floor?
Good morning, honorable judges, fellow contestants, and esteemed guests. I'm the reviewer from Team Wiggle, and right now I'm going to review a ruler cannon. So here's the problem statement of the ruler cannon, and focus on those main focus next. And here's the phenomenon and the theory and the experiment that the reporter used next. And here's some pros and cons for a reporter. So I think for pros, they have good complete theory explanation, and also they have clearly demonstrated their phenomenon. And for cons, I think they lack of error rates in their graph, and they also lack of elaboration of how the frictions influence the whole system. And for the pros and cons for the opponent, so they point out several little mistakes the reporter have and delve further into those their concerns. And for the cons, they fail to elaborate on the cantilever beam that we discussed before. So now I'm going to summarize the discussion for the opponent and reporter. So when the opponent asks the reporter, can you make sure the force given by the iron ball, and how do you measure the time interval? And the reporter said yes, they can measure the force and by using the experiment and empirical results. And they also use tracker. In our opinion is that, okay, next. So next, the opponent says when you are measuring the coefficient, that you should use different n to make sure the result is accurate. And the reporter agreed with that, and our opinion is that yes, they should use different n to make sure it's accurate. So for discussion number 4, the opponent said why is a proportional work like that, and it should be correct to your mv times the to the power of 2. And the reporter says they use mathematical formula for the calculation, and yeah, that's a kinetic energy formula. And next, the opponent questioned about the consideration of friction with the floor or the wooden board. The reporter says it's negligible. And next one, the opponent says they need to consider the initial potential energy, and the alpha should verify when using different material. The report says it is considered already, and the alpha is tested but did not put it on the presentation. In discussion, the opponent says the shape and the material can be future analyzed with things that are easier to analyze, and the reporter agreed with that. So next, I'm going to talk about the discussion that asked both of them. So first, I asked him about the coefficient of friction influence on the experiment. So the reporter, in the presentation of the reporter, he says that whenever the coefficient of friction increases, the velocity will decrease. However, he also mentions that the reason that the system can store the energy is because there's friction. So in our opinion is that when the friction there's a boundary condition between the friction threshold and the velocity when the ball is ejected. Since a bigger friction threshold can actually store more energy in the system, so it can therefore increase the ejection velocity. However, if the friction threshold is large enough, it will prevent the ball to launch. Next, I asked them about how do you calculate the bending moment. So they say it's shown in their presentation, but I can't really fully understand that. In our opinion, is that bending moment is the integration of every point of applied force times the length of the length of the applied force, which equals to their torque. And since the bending moment can only test it when you apply the specific point on it, so you can't really use since the ball area of the contact area between the ball and ruler is large enough, so I don't think it actually can use the bending moment to calculate this phenomenon. And next, the energy consideration. And so we think that also like when the ruler are not fully closed, there's some loss of energy, and the reporter agreed with that. Here's some missing point.
Okay, concluding remark from reporter.
Now let's talk about concluding remarks. First, to clarify, we don't consider the friction coefficient as a constant under different normal force. Second, regarding to the opponent, we believe we conducted enough experiments and showed enough data to make our analyzation and calculations valid. Third, we can ensure and quantify the forces exerted on the rulers. Fourth, we consider the initial potential energy and the kinetic energy of both rulers and projectiles, and also the energy dissipation above mentioned. So the formula we use are appropriate. 5. Neither the projectiles or the ruler touched the wooden board when we conducted the experiment. So there wouldn't be any friction that needs to be considered with the contact area of the wooden board and the ruler. And 6, the reason we didn't show the experiment using a plastic bottle cap is the irregularities around the surface of the plastic bottle cap alters multiple parameters at the same time. However, we did conduct the experiments to analyze how is the ejection speed different from the different round projectiles. And finally, we consider the energy losses. This including the damping and the lunar restoring energy when the round projectile is already ejected out of the system. And that's the end of the concluding remarks. Thank you.
Okay, now for theory and the focus on Okay.
Maybe I have one. So there's something I'm still missing. Okay, so you use this, you basically use the energy conservation, of course, total energy conservation, because you include the dissipation. But my question would be like, since you basically use these 2 iron balls to hit the ruler and try to bounce the ball, okay? So then my question is that, okay, maybe I can also ask 3 of you. Then do you think in this process, if you consider everything in a total system, does the momentum conservation law will hold?
Well, the theory we use is mainly describe when after the iron ball strikes on the surface of rulers, the deformation of the rulers. So in our theory, we didn't really consider the momentum of the iron
So
ball.
you think the momentum conservation will not hold?
Yes, it will affect the deformation of the rulers, and we consider the energy transform will be the potential energy of the ruler after the striking. And
No, I'm just asking the momentum. I'm not asking the other.
yes, we think that's one of the influencing factors.
But I'm just asking whether you will hold or not.
Can you?
Whether the momentum conservation will hold.
Well,
To be true. Whether the momentum conservation law is valid in your experiment.
yes.
You think it is? Yes, okay. Then how about in his experiment?
I think it's not true because the velocity of the iron ball and the velocity of ping pong ball is at different direction.
Okay.
Yeah, also, I don't think that the momentum is conserved.
Why?
Why? Because there's some, like obviously there's some energy loss during the process.
The momentum conservation law is irrelevant with the energy.
Can you repeat it?
Momentum conservation law is irrelevant with energy.
Like since the ruler will not hold, I don't think it will come.
Another question?
So I will ask a quick one. For the reporter here, I would like to see could you show me the slide about you showed me you show the value of your acting force, F1, and the acting time. There is the table, is that table from your slide?
Okay.
The acting time and acting force. The data table, I think. Yeah, this one. So the rebound force is your iron ball's rebound force, is that right?
Yes.
So I mean, so the force you measure here is obvious. It should be F2, is that right?
Yes.
So how do you get this value? F2. You use what you quite. As I'm guessing, you are using the impulse will be equal to the change of momentum. Is that correct?
Yes.
So in that case, you assume the contact point there. It's the ruler there is a hard surface. Is that correct?
The rulers has the hard surface. Do you mean after, like when the round projectile is inserted between the rulers?
I mean, when the iron ball that strike the ruler on that point, on that point, is your ruler a hard surface or not?
It's a hard surface, but it can have since we have measurements on Young's modulus, so we can know the the coefficient of highly deformed. So yes, it's a hard surface.
It's a hard surface. So could you go back to page 11 or 11 first? Let's try 11. But you indicate F2 there. There is a space difference.
Oh, sorry, I'm misunderstanding the jury's question. I found you are asking the materials of the rulers is hard or not. And to corresponding to the jury's question, yes, that is a surface for the rulers to deform.
Yeah, so which means the ruler here will have a very slow velocity. So I don't think the surface there is actually a hard surface. The way you calculate F2 is kind of say uncertain now.
I understand the jury's point.
So how could you defend your idea? I mean, you're facing my challenge here.
Well, by the impact velocity and the rebound velocity, and we have done many measurements on the impact velocity on the surface of rulers and the rebound velocity of the rulers. So we think the force acting by the pendulum can be minimize the deviation since the juries have mentioned the problem.
Okay, I will take that.
Okay, now. Okay, for the reporter. Okay, 7, 7, 7, and 6. And for the opponent, 7, 6, 6, 7, 6. Okay, for the reviewer, 7, 4, 6, 7, 7. Okay, so we close this section.